Okay, what we studied last time was we studied Sine-Gordon theory. And in Sine-Gordon theory, what did we see? We saw, besides the perturbative spectrum, which is mesons, we have meson or meson of mass m square. That's the excitation around each. So we have infinitely many ground states, so excitation around each of any one of them, because they are equivalent classically. So that excitation has the standard mass m square. We had the potential. What was the form of the potential? Potential was m square by beta square 1 minus cosine beta phi, or something of this kind, right? And if you expand around any of the ground states like phi equal to 0, so you will have a term which is half m square phi square. So this is the mass of an excitation around any of this bottom of the potential. For example, phi equal to 0. And then we had non-perturbative configurations, and those were solitons and antisonitons. Non-perturbative means that they are not excitations around a vacuum, a particular vacuum. They are configurations which interpolate between two vacua, two ground states. So they are non-perturbative. These are non-perturbative. These are non-perturbative finite energy, because we calculated the energy for those solutions, mass, finite mass, finite energy, static configurations. And these interpolating between two ground states. And configuration was something of this kind. This was soliton, phi, beta phi as a function of x. Now, this is beta phi equal to 0, this is beta phi equal to 2 pi, or configurations which were this kind. This is 2 pi, this is 0. Soliton and anti-soliton, soliton bar. B, these configurations, the mass or the energy of these configurations was dx of d phi dx square, something of this kind. And that turned out to be some value. I don't remember the value. What was that? 8 by m square by beta or some such thing. Beta. This, 8m by beta square. Yes, that's what this is. And what does this tell us? This tells us that the mass density or energy density is d phi by dx square. So, the contribution to mass comes from the region of the configuration where derivative with respect to x is large. That is where most of the density lies. And the derivative of this configuration is large around the 0, because the derivative here is almost 0, or as it climbs it is very small. Here again derivative is small and asymptotically it is 0, but it is in this region that the derivative is largest. Therefore, mass density is concentrated in this region. So, these are localized because the mass density is largely contained in a localized interval. So, these configurations have the property that they are finite energy, static solutions of equations of motion, and they are localized. And they carry a topological charge. Plus minus 1. Plus 1 for soliton, minus 1 for anti-soliton. This is what we saw. Now, today what we will do is that we will study non-abelian theories, non-abelian gauge theories, gauge theory, a particular non-abelian gauge theory with similar topological solutions.
Here, you could have had solutions which interpolated between 0 and 4 pi, minus 2 pi. Are those solutions as well?
Now, the question is, you can check and see if they are solutions, which means 2 soliton, topological number q 2, 3, 4, 5, or plus minus 2, minus 3, minus 4. Are they solutions or not? And if you study them, you should come to a conclusion that they are not solutions except in the limit when the separation between these two solitons, because these the configurations you are talking about is something of the kind, starts from here, goes to one vacuum, goes to another vacuum. It could be this kind, or it could be this kind. The ones that are solutions are of this kind. With this is the center of these excitations. These excitations in the limit of infinite separation. So they become better and better solutions if you start separating them. Otherwise, they are approximate solutions. They are not solutions in this theory when these two objects are close by.
The Clothesline model.
Yes.
I mean, there isn't any reason to not expect these clips to wind around twice before.
Now, they could wind up toward, but their energy will not be minimum. They will not minimize energy except when you make the centers to be very, very, I mean, they will start getting closer and closer to minimum of the energy when you, which is means that there is solutions. They will be solutions in that approximation.
So they don't saturate that bound which we wrote down.
Yeah.
Mass greater than equal to T.
No, they will saturate because there will be twice
No, in
twice
the
T.
finite limit they will.
Yes.
Otherwise,
Yes, indeed. Okay. That's a good question. All right, so let's do non-abelian theory, and we'll discover that magnetic monopoles in this theory will be the topological solitons. So let me set up the theory now, the model. The model is known as Georgi-Glashow model. It has gauge invariance SU2. And contains therefore gauge fields A mu, where this is the SU2 index and A runs 1 to 3. Besides that, it has real scalar fields in triplet representation of SU2, phi A, A1 to 3. Triplet representation is also the adjoint representation for SU2. The action is given by d4x the gauge field action, which is square of the corresponding field strength, and field strength is the anti-symmetrized derivative of the gauge potential, and ABC and the nonlinear term. With the coupling E, we call that coupling, earlier we called that coupling G, we'll call it E here. And I don't know, I remember whether I put it plus G there and now I'm putting minus E here. Then we have the P's for scalar fields, half d mu phi A d mu phi A. What d mu is the covariant derivative. D mu, capital D mu phi of A is d mu of phi minus epsilon A B C of A mu B phi C. I hope I have the signs right. Yes. And in addition, we have a potential for the scalar field, some V of phi. So that's the action for this model. And the potential has a form V of phi, which is lambda by 4 phi b minus a square. Now there is a little bad notation. This b is the SU2 index. B runs from 1 to 3, and repeated B means sum. This A is not the index. This A is a constant. Yes, whole square. Huh? Now I have done it like this, maybe. So I have, so remember this is bad notation. Maybe I could have called it V. Normally call it V, right? I think soon I'll not write A as the index in most places. So this confusion does not arise. All right. Now, like we said here, F mu nu A phi A and covariant derivative of phi A are all in adjoint representation, that is triplet representation of SU2. And this action is invariant under SU2 transformations. So we have invariance under SU2 gauge transformations. And that's not much to check, because once we realize these objects are all in adjoint representation, because covariant derivative of phi has been constructed in such a way that phi covariant derivative of phi transforms the same way as phi. That's what definition of covariant derivative is. So they all transform the same way. Then squares of these this is made up squares of these objects. Squares of these objects are invariant under the SU2 transformations. Is it clear? So there's nothing. Once we realize that, invariance is obvious. Equations of motion, this theory. You just do the Euler-Lagrangian equations of motion for this theory, do the variation with respect to various fields, or covariant derivative of field strength. Mu contracted, B is E times epsilon BCD phi C covariant derivative, covariant derivative nu up of phi D. So now I have not used A as a label to avoid confusion. These internal space indices A, B, C that I have, I will raise them and lower them freely because it doesn't matter. But space-time indices, mu nu, raising and lowering has to be done with the our conventions for this are through a metric which is plus, minus, minus, minus. It is diagonal with plus 1 entry, minus 1 entry, minus 1 entry, and minus 1 entry. That's the signature of the metric. And this covariant derivative on F is the same way defined as the covariant derivative on phi, which means covariant derivative of F alpha beta A is the ordinary derivative of F alpha beta A minus epsilon, or maybe let me call it B now, B, B, C, D, A mu, C, F alpha beta. So that's how this covariant derivative is here. So this is the equation of motion that you obtain from this by varying with respect to the gauge field. Then there would be equation of motion that you would obtain by varying with respect to the phi. And that equation of motion is d mu of phi b is equal to minus lambda phi square minus a square phi b. Now these covariant derivatives, this one is already defined the way we have defined somewhere here. The second covariant derivative is also defined the same way, except that you replace this phi by the covariant phi in these two places. So these are the equations of motion. In addition, we have another equation which is Bianchi identity. It is not an equation of motion for this action, but it is true by the way we have defined the objects. It means it's an identity, which is that the covariant derivative of what we call f dual A is 0, where f dual mu nu A is 1/2 epsilon mu nu alpha beta f alpha beta, or let me call it again b. And that's an identically true property, because we have defined f through this combination and dual of f by multiplying it by an epsilon mu nu alpha beta, which is a completely antisymmetric 4 tensor with values +1 or -1 or 0. This is a small exercise. Check that this identity holds. Check that this identity holds. Check that this identity holds, which means put in this definition and then take the derivative of this. Sometimes you may have noticed that this identity is written in a way that d mu f alpha beta b plus cyclic combination, cyclic interchanges of the space-time indices is equal to 0. That's another way of writing the same identity. Next interesting object for this theory is to calculate the energy momentum tensor. And from there we can calculate the Hamiltonian. You can calculate the Hamiltonian by going to the canonical formulation and looking for what are the various canonically conjugate momenta to the fields we have, which means to A and to phi, and then write the standard method of finding a Hamiltonian. Or you can do an equivalent way of finding out Hamiltonian by finding out what is the energy momentum tensor. And I'll tell you a trick of how to get an energy momentum. There are many ways how to get an energy momentum tensor. And the trick is, we set up this theory in a flat space-time, where the metric was, space-time metric was this object. plus 1, minus 1, minus 1. Introduce a space-time dependent metric. You've been doing a course on gravitation also, right? You should be able to see this trick very quickly. And if you introduce G mu nu, then a general coordinate invariant way of writing that action is 1 by 4 G mu alpha, G nu beta, F mu nu A, F alpha beta A. That is the first part. And this G, let me write this G. This G is determinant of the metric. And minus G because determinant of this metric is negative. So you put minus G in the square root. And then we have 1/2 G mu nu d mu phi A d nu phi B, let me call it B, B, phi B, and then minus V of phi. Then the energy momentum tensor can be calculated, and let me call it theta mu nu, by calculating the variation of this action with respect to G mu nu x. Minus twice. So that's the trick. And since you may have done these things, let me give you a few steps. Variation of G mu nu up, yes, the G mu nu up here is inverse of G mu nu down. So inverse means that this times this is so the variation of the inverse, which is sitting here, 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 and here, is minus G mu alpha, G nu beta times variation of G alpha beta. And then G is sitting here, which is determinant G, and variation of square root of minus G, determinant of the metric, is half. What is the answer? Half, right? Yes. Half square root of G times G alpha beta, variation of G alpha beta. You should be able to work it out. This is elementary exercise, if you have not done it already. And use this to calculate theta mu nu. Yes, that's correct. And if you do this exercise, you should be able to, this is an exercise, so get the answer. The answer is that theta mu nu up is FB minus FB mu alpha, FB nu up alpha down. Plus d mu phi b d nu phi b minus g mu nu up the Lagrangian density. Lagrangian density is whatever is inside the integral in action. These two parts come from the variation of these inverse matrix here and here. The last terms comes from variation of the determinant G, G mu nu Lagrangian density. And then just put back that Lagrangian density into this and calculate the 0, component of that. 0, component of energy moment tensor is yeah. So after you calculate that the 0 of that is the energy density. And since we are working in flat space time, now you put G mu nu back in equal to eta mu nu. So that gives you the theta 0, component gives the energy density. And if you do this algebra, the answer is EBI, where EBI is same as EBI down, right? Because space like indices, whenever they go up and down, there is a minus sign. And that object is FB0I. So the square of this object plus square of BI and capital B, BI is same as capital B I down, and that is minus half epsilon I jk f jk. Now you may have already recognized it, is that this essentially is kinetic energy of the gauge fields plus the potential energy of the gauge fields. So that's what Hamiltonian is. Or if you were doing canonical Hamiltonian analysis for this theory, this E that we have here is the canonically conjugate momentum of AI. This is canonically conjugate momentum field associated with ABI. So this piece is corresponding pi, the canonical conjugate momentum square. Then we have from this object what I'll call it pi AI BI times pi BI, where pi B pi B is covariant derivative 0 of phi B. This is the covariant derivative in the time direction. because 0 is the time direction of phi square of that object, and that is also canonically conjugate momentum field to phi A or phi B. Then we have d I phi B d I phi B. So this is kinetic energy of the scalar field written in a covariant form. This is the potential energy. So kinetic energy plus potential energy, that's what a Hamiltonian is. And then plus B phi. So half of this expression plus P phi. P phi is the potential energy density. So that's our energy density. Or Hamiltonian density, and space integral of this object would be the Hamiltonian. d3x integral of this object is the Hamiltonian. So let me also give it maybe another symbol, that it is the Hamiltonian density. Notice one nice property of the Hamiltonian density. Energy density theta 0 0 is positive definite, is positive. That is theta 0 0 is greater than 0. That's because it is square, sum of squares plus V phi. And V phi, the way we had written it, was positive, because V phi was lambda by 4 phi B minus A square and square. So it's sum of positive quantities, so it's positive, or at best 0. At the lowest, 0. And since it's sum of the squares, the smallest value that the energy density can have is 0. So the smallest, which is equality, smallest value given by equality is theta 0 0 equal to 0. And theta equal to 0 means that because these are all sum of squares, each term is 0. Each term is 0 means, and square, therefore each E is 0, B is 0, pi is 0, covariant derivative of phi is 0, and V phi is 0. Now if E is 0, B is 0, that tells me F mu nu B is 0. For the minimum. So is d mu phi, because pi naught is the time derivative, covariant derivative of phi, and this object is the space derivative. So both of them are 0, so that means d mu phi is 0. And also v phi is 0. And for such configurations, theta 0, 0 is 0. So these are the minimum, these give us the minimum of the Hamiltonian density. Now what are the possible solutions for these equations in terms of the fields that we had to start with, which is A and phi? Now these correspond to, for example, A mu is 0. And these also correspond to this object being 0, v phi being 0. That is phi b equal to a square. Right? So a configuration where gauge field is 0 and the scalar field square, scale is a triplet, so the length of this triplet in the SU2 space is a constant given by a square, the parameter that we had introduced in the potential in the theory. So this defines the ground state or vacuum. See, vacuum is a quantum mechanical concept. Ground state is a classical concept. But somehow we'll use them interchangeably even when we're discussing classical mechanics. But the corresponding statement would be that there is a corresponding quantum state for this configuration, which would be called vacuum in the quantum theory. So this is the ground state or configuration. It has the smallest energy, which is in this particular model exactly 0, classical energy. Now let me take a particular solution of this equation in the form a particular solution. Which is that phi b is equal to a times delta b, what direction I have to put it? 3. Which means phi b is a vector in the internal space, in the SU2 space, with components 0, 0, and a. Right? If I want to write it in terms of a vector, it is 0, 0, a. There is a component value a only in the 3 direction in the internal space. That is a particular solution of this equation. All right. Now, any gauge transform of this solution, so this phi, so if I just go from this phi b to another phi b prime, through a gauge transformation. A gauge transformation is an adjoint representation of phi. This will transform like an adjoint representation. An adjoint representation means it would just be it would simply be a rotation, ordinary rotation in the internal space. So if you think of as vector in 3 space, do an arbitrary rotation. That's what a gauge transformation does. But then this phi prime that I have obtained from this configuration is still going to satisfy this equation, because phi b is a gauge invariant combination. Is it clear? Every gauge transformation of this configuration still satisfies this. So phi prime b is a square. Hence, all such configurations represent the ground state. So to repeat, ground state is given by this vector with component 0, 0, 1, or any gauge transform of it, any arbitrary gauge transform of it. But we may decide to work with one of such configurations as the ground state. In particular, I may work with this one, or I make a particular gauge transform of this one, that is also a good one, a particular one. So any one member in this class I could take as my ground state and then try to study the dynamics of various fields around in that ground state. In particular, I could just choose this one. So if we choose phi b equal to A times delta B3 as our ground state, and then study the dynamics of various fields in this, around this ground state, then we would have, that dynamics would not have the full SU2 gauge invariance. Because this object on its own is not gauge invariant. Under gauge invariant, it changes to gauge transformation changes to phi b prime. Right? Of course, I could always do something is that do a gauge transformation of this object and then get by a particular amount, do a rotation in the internal 3 space by a particular amount means by a rotation in 3 spaces described by 2 angles, by certain specific values of those 2 angles. That will be a particular rotation, and get a new phi. And I could make the expansion around that also. So the dynamics around doing that also will not have the full gauge invariance, but it will not have any new physics. So physics would be the same whether if I develop the theory around any particular point in this ground state. But once I have chosen that particular point, the symmetry would be reduced in this sense now, see, reduced or broken. The word broken is a very bad word for this. So that's why I'm spending a little time to this. Broken sometimes means as if the symmetry is gone. And well, it is gone in some sense in the description of your theory. But it doesn't matter if you could have gone to another vacuum on this member and gotten the new physics. That physics would be exactly identical to the physics that you had done earlier. Physics there means masses, couplings, those are the objects, physical objects, degrees of freedom, spectrum of the Hamiltonian, energy. They would not be different, but the description would be different. So there's a name given to this. This is symmetry would be smaller. In fact, symmetry is U1, and this is called spontaneous breakdown of symmetry. Spontaneous breakdown of symmetry from SU2 to U1. Better word would have been, instead of saying spontaneous breakdown, it spontaneously hides the symmetry. So hidden symmetry. I think that is a better word. So it is hidden symmetry. Or hidden invariance. In the sense that I was describing, is that if I do develop the theory around any one member of this class of ground states, the physics that I would get would be the same. So in that sense, the symmetry invariance is not really lost, but it gets hidden in the description that I develop. Yes.
I said that gauge is fixed partially using this phi p equal to E.
Yes, that's also a way of saying it. Right? So when you say spontaneously broken symmetry, this is what you mean. This means that it is the property of the ground state that you have picked up to describe your theory, as opposed to some symmetries that are broken because the Hamiltonian itself is not symmetric. See, Hamiltonian here is symmetric. So I could have a theory which has an Hamiltonian which is not symmetric. I had some term which is not symmetric. That would also be a breaking of symmetry. But that is not a spontaneous breaking, because that is a genuine breaking, because the Hamiltonian is different. So in that theory, different gauge transforms will give me different theories, different physics. Wherein in this theory, I don't get different physics. So that's the reason I say sometimes using the word breakdown is not perhaps correct. When we say the symmetry gets hidden is a better word. But we normally use spontaneous breakdown symmetry. I'm spending a little time on this because one of you asked me that we wanted to do spontaneous symmetry breaking better, right? Otherwise, this is all what you learned. So all these configurations, will give them a name. This class of configurations which describe the ground state will give them a name, and we'll call them Higgs vacuum. Or some of those people who like to be very mathematical in their language, they give it a name, another name, they call it Higgs moduli space. Is all configurations, is the space of all configurations which minimize the Higgs potential. Higgs potential is a name given to what we call V phi. So we can represent this moduli space of M of H is all set of phi's, so that V phi is 0, or in a phi A, phi B is A square. In particular, we can take phi's to be constant. So I mean all configurations, all constant configurations, let me say. And if phi is a constant, and phi B is A square, which means phi 1 square plus phi 2 square plus phi 3 square, because this object means phi 1 square plus phi 2 square plus phi 3 square is A square. This represents an equation for something we are very familiar with. It represents the equation for points on a two-dimensional sphere. You have a ball of radius A, and the surface of the ball is an S2 two-dimensional sphere, and the points on that surface are described by this equation. So the moduli space of the ground state, or Higgs moduli space, is described by points on S2. It's an infinite dimensional space because points on S2 are infinitely many. And from one point to another point, you can go over by an SU2 rotation. So that was a description of ground state. Now we are interested in configurations other than the ground states, which means configurations which solve the equations of motion that we listed earlier, or equivalently configurations other than the ground state which minimize the Hamiltonian, the energy density. We are interested in looking for such configurations, like we did that in Sine-Gordon theory. We looked for what we later call soliton solutions. So we are interested in looking for solutions of that kind in this theory. So in addition to this particular finite energy solution, which has energy 0, we are interested in finding out other finite energy solutions, finite energy asymptotically, which means for large boundary of the space, for large x, they must asymptotically lie in the Higgs moduli space, in the that's what we saw for solitons. The solitons were interpolating from one ground state to another ground. At the boundary values minus infinity, plus infinity, they were ground states. So what we're looking for, we're looking here again for solutions which at the boundary of space at x minus infinity, plus infinity, y minus, we are 3 space now, y minus infinity to plus infinity, z minus infinity to plus infinity, or if I go to radial coordinates, r infinity. At r infinity, they must get values which are some point in this S2. So asymptotically means, let me know, at spatial infinity. That's what we mean asymptotically here. Now I want to give you this one exercise. This exercise, you have learned it in your course on maybe first field theory course or standard model. Did you do standard model course? You did. Somebody told me you did SU2 cross U1 electroweak theory. So you did spontaneous symmetry breaking there, and you would have studied the structure around a particular vacuum of various configurations. So that exercise I want you to repeat in this context. So what is the exercise? Let me define the exercise. Rewrite the Lagrangian density or action. Action is the 4 integral of Lagrangian density by expanding around this particular ground state. So we write phi b is equal to phi b vacuum, where phi b vacuum is A delta B3 plus some object, we'll call it HB. So the Lagrangian density that you had, we have rubbed it off. Rewrite that by making this expansion. This is about this particular choice of one ground state. Okay, and of course, A ground state is A equal to 0, B equal A equal to 0. So you expand means that around 0 also A equal to 0, but that means just you write A as it is A. But phi you write it as phi vacuum plus an HB. And if you do that, show one, that gauge field A mu, the component 3 in the internal space, in the SU2 space, is massless. To start with, there were no mass terms in the Lagrangian for gauge fields that you had, right? So A mu 3 in particular was one of those gauge fields out of the 3. That gauge field will still not have any mass term. Mass term means will not have an A3 square term. So it will be massless. And it's massless, and since it's massless, we'll identify it with the photon. Photon of this theory. So that is one. Second, show that gauge field, the other two gauge fields, let me combine them in a particular complex combination of W mu square root half A mu 1 plus minus I A mu 2, and call this object plus minus. I don't know why I have called plus minus here and minus plus here, maybe. There must be some reason. So, the gauge fields, the other two components, rewritten in these complex combinations. These complex combinations is each other's complex conjugate. These objects become massive. With mass values for these m plus minus 1 equal and given by A times E. A is the vacuum expectation value. A is the parameter that parameterizes the vacuum expectation value, and E is the coupling constant that we have introduced. So, which means what you will see is that you should be able to generate, when you expand it right this, you should be able to see a term of m plus minus, which has the same value for both of them, as W mu plus W mu minus. A term of this kind will tell us that you have a complex gauge field with mass m, or complex gauge field we talk about as two fields, right? And with respect to, see, now we said that this choice of vacuum expectation value spontaneously breaks the gauge symmetry from SU2 cross U1. And U1 gauge symmetry would mean that the corresponding gauge boson has to be massless. And that's what we have identified, that A3 is that one massless, and that's what we call it photon. So, that A3 is the gauge field, of unbroken U1, the leftover U1. And with respect to that U1, these gauge fields that we have constructed, W plus and W minus, have charges. And show that W plus and minus have U1 charge plus 1 and minus 1. And that's the reason I think I have plus 1. Maybe it's this combination which has plus 1 charge, and this combination has minus 1 charge. 1 means 1 in the units of E, so it will be E. How do you find out what is the charge? You find out through finding out how it couples. W mu plus minus couples with the photon, because charge is measured by the strength of the coupling. So, you just isolate the terms which are A3 times W plus W minus, because that gives you the interaction of W plus and W minus with the A3, and A3 is the photon. Coefficient of that object has to be plus E or minus E. All right. Or in other words, when you rewrite this in terms of these fields now, you would have terms which will have derivatives of W plus and W minus. Right? From F square terms, you will capital F square terms, you should be able to extract out d mu W plus times d mu W minus, these terms. Now, for U1 gauge invariance, these must be covariantized. So, you must get them in a covariantized form with respect to the U1. which you will get, which means the derivatives must come in a combination that d mu plus E times A mu acting on W plus and d mu minus E times A mu acting on W minus. You just have to discover that that's the structure that is emerging. If that structure is emerging, then you identify the charge. Is that clear? So that is one. Now last one is that last property that you must get out of this exercise. So that was what? A, B, C, D. So D. You will find a neutral scalar field H3, because H3 is one of the components there, right? H is H1, H2, H3. So take the three component. This would be neutral under this U1. So that's why neutral, which means this will not have the U1 charge, which means the derivative that acts on this in the Lagrangian density, because there will be square of d mu h's, will not be covariantized. There is nothing, no covariantization needed. There will be no coupling of photon A mu 3 with H3. So this neutral scalar field, field, and we'll give it a name and call it Higgs field. Sometimes we call phi also Higgs field, and sometimes we call this an Higgs field. But this is the physical Higgs field, because we're looking for the spectrum, right? So this confusion, you said this is the physical Higgs field that would be seen in an experiment if this was the theory of nature. This Higgs field with mass mh is twice root 2 lambda times A. Lambda was the strength of the potential, V phi, and A is the expectation value of the Higgs field. This is the mass. This is exactly the object that in SU2 cross U1 electroweak theory that you have studied, and we call that Higgs, and that's the Higgs that everybody is hunting around in Geneva these days, because we want to discover that. So this is the counterpart of that physical Higgs in this theory, and it has a mass. Then the last one, this H field that we had introduced here was a 3-component field, triplets. So H3 we have interpreted as a physical field with a mass. What about the other components, H1 and H2? So the question is, what happens to other components? Does anybody know what happens without having to think about it? Because you've done electroweak theory. There also something of this kind happens. What happens to these two components? Where are they? They somehow don't have any special physical content. Well, they have some physical content, but they don't have any independent physical content. What happened to them? Somebody says eaten up by the gauge bosons. What does that mean? Yes. We discovered that W plus and W minus, we'll discover doing this exercise, have mass. So we have vector fields which have mass, which means vector fields which have mass don't have only transverse degrees of freedom. Vector fields which don't have mass, like photon, have only transverse degrees of freedom. Massless vector fields are two-dimensional representations of Lorentz group. Have only two independent components, not two-dimensional, but two independent groups, two different degrees of freedom. But a massive vector field, vector under the Lorentz transformations, has three independent degrees of freedom. Two of them transverse, and the third one longitudinal. So for the photon, the longitudinal degree of freedom is a gauge degree of freedom. It's not a physical degree of freedom. But for a massive vector field, longitudinal degree of freedom is a physical degree of freedom. But somehow we started with a theory, all degrees of freedom have to lie in this theory that we started with. This W has now three physical degrees of freedom as opposed to massless gauge boson, massless vector field. So it needs an extra degree of freedom in order to be described as a massive vector field. And that extra degree of freedom cannot come from anywhere else except in the theory. And those extra degrees of freedom are H1 and H2. Is that clear? So they get absorbed in the definition or in the degrees of freedom of the massive W plus and W minus. Or sometimes he used the word, they get eaten by W plus and W minus. And that makes them fat, and that's why they are massive. Okay, so this exercise, please do it, and if you have difficulties, come back. Huh? Okay, one more exercise in this context. F. I have said this in words so many times, but do this little bit of mathematics with it. Let me define a generator Q, which is E times T3 H cross. T3, T1, T2, T3 were the three generators of the adjoint representation in terms of matrices that if I write. Right? 3 cross 3 matrices, three of them. I take the third one and construct this object. The three generators of SU2, what do they do? Is written in terms of adjoint representation. Adjoint representation is written in terms of 3 cross 3 matrices, like angular momentum, right? Ordinary angular momentum rotation. J1, J2, J3. So here I've called them T1, T2, T3. What do the J1, J2 do for ordinary J1, J2, J3 ordinary angular momentum? They introduce rotations in different planes, 3 planes. J1 introduces rotation in 2-3 plane, J2 in 3-1 plane, and J3 in 1-2 plane. Same way, T1, T2, T3 introduce rotations in this internal 3-dimensional space, because we have 3-dimensional internal space, SU2. SU2 adjoint representation is defined by 3 objects. 3 labels A, B taking value 1, 2, 3. So T1, T2, T3 are rotations in these internal 2 planes, 1, 2, 2, 3, and 3, 1 plane. So T3 is an object which introduces rotations in 1, 2 plane in internal space. If it introduces rotation in 1, 2 place, then this leaves Is that clear? Because this object introduces rotation only in the first two entries, and the first two entries are 0. So therefore, it does not change it. And is this clear? And that's the reason I gave it the name Q, because this is the generator of the leftover U1 invariance. Right? Because T3, you remember, vacuum expectation value in 3 direction, A3, it was all, they were all in 3 direction. So this is the generator of U1 transformation. So what I have said in words, you derive it. That's the exercise, that this object leaves this invariant. Show that that's true. How are we doing with time? Oh, we are almost through, right? 5 minutes. Now what should I do? Okay, let me start the discussion of monopoles, and then we'll see. Next time we'll go ahead with it. So this was now, we studied the theory around a vacuum and worked out its spectrum around a vacuum. And spectrum was a massless photon, massive charged vector fields, and a neutral scalar Higgs field. This is the spectrum of the theory around a vacuum. So this is the perturbative spectrum theory. Now we are interested in configurations which are inherently non-perturbative solutions of equations of motion. So we want to find out so those are the monopoles. So let me say monopoles, magnetic monopoles. Monopoles in this theory. We are interested in static time independent configurations. Static field configurations with magnetic charge. Now energy density for these objects would be what we have written earlier, or energy now, let me write an integrated form, d4x, d3x, half was E square plus BA square plus pi B square plus D I phi B square, call it B plus V phi. This is what we had found earlier. We want configurations which will have only magnetic charge, no electric charge. So if we want objects which have no electric charge, we want objects for which EB is 0. No electric charge. Now what is EB? EBI was minus FB 0I. And this object is D0 AIB minus DI AB0 minus E BCD A0 AICD. That's what the field strength 0I component is. And we want this to be 0. How can we make it to be 0? And we also want static configurations. Static configuration means this is 0 because of static configurations, time independent configurations. Then further I want these terms also to be 0 because I want AB to be 0. So that tells me this equal to 0 tells me that A0B is 0. So 0th component in the time component of the gauge field is 0. So that this is 0, so that this is 0. This is 0 if A0 is 0, because the A0 is sitting in both these places. Of course, if I take a gauge transform of A0, that will also give me a 0. Is that all clear? So I have taken one member of that class of gauge transforms. Clear? And for such configurations, now Hamiltonian density or energy or mass is d3x. This energy is mass. We are working with C equal to 1 units. Then energy is mass. Static configuration at rest. Is simply that this object is 0, this plus this object is. Now what is pi? Pi was time derivative of phi, covariant derivative, that is d0 phi a b b epsilon b c d a0 c phi d. Now we just think of static configurations, so this is 0 because of static configurations. This is 0 because A0 is 0. So pi is 0 for such configurations. Therefore, for such configurations, mass would be given by half BA square plus half DI phi A square plus Is that clear? Is that for static configurations which don't have any electric charge, the mass would be given by half of BA squared, half of DI phi squared plus the potential, integral d3x. Now, let me rewrite this expression in a particular way. Rewrite m is equal to d3x half b plus di phi b b I plus da phi b this times this is the first term, this times this is the second term. But then I have cross terms in this, which I have introduced by hand. So let me subtract them out. Right? I've just rewritten that expression. The cross term is exactly this object. This times this times this, two of them and half is there, so I subtract it out. I could also rewrite this expression by taking the minus combination here. Then I would have added the cross, subtracted the cross term. So I'll add it up. Now, this is square of an object. Therefore, this is positive, and therefore integral of this object is positive. V phi is positive because it was the way it was written, it was square of an object. So this is positive. So if I drop this positive term here, then this object is clearly bounded by one half d3x ba phi plus minus da phi b put this square bracket square plus minus d3 x bai. I just dropped this term, a positive term. Now look at this term, d3x ba phi d covariant derivative of phi. Let me use b here. I don't know. I can write this. This is a covariant derivative on phi. I can do partial integration. And the nice property of covariant derivatives is that under partial integration they behave like ordinary derivatives. So I can shift this object onto this. That will give me a covariant derivative acting on B. But covariant derivative acting on B is That's Bianchi identity. Excuse me, sorry. Let me switch it off. This is Bianchi identity, which we checked in the beginning. Bianchi identity. So this is 0. So which means when I do partial integration and shift it onto this, that piece is 0. But there is a piece which is a total derivation of this combination. And that is ordinary derivative d of b phi I phi b. This guy is not letting me off the hook. Is that clear? This object I can rewrite by partial integration as a total derivative and a derivative on b, covariant derivative on b, and covariant derivative on b is 0. So that's what this is. This is not, I could put covariant derivative here also, but I put an ordinary derivative. And the reason is very simple. The object here is gauge invariant. Derivative, covariant derivative on gauge invariant object is the same as ordinary derivative, because this does not transform under SC2 transformations. It has no SC2 charge. There is no covariantization needed. Okay? So this is an ordinary derivative. Now this is not an ordinary derivative, it is a divergence of a vector, because this is in ordinary space, this object is a vector I, this is a divergence of a vector. I can use Stokes' theorem to convert this volume integral into the surface integral. So I'll rewrite it now as dSi of phi bi phi b, where dSi is an element on the surface at the boundary of space, because there was space integral, and boundary of space is an S2. So S2, let me call it infinity, where S2 is the boundary of the space at infinity. So S2 infinity is an S2 at R going to infinity, the radial coordinate going to infinity. And this is Stokes' theorem. I think we're getting a little too late now, right? Maybe I'll stop now here, just at this point, and we'll pick it up on Monday again from here. Huh? Because in order to get to something reasonable, I need another 10 minutes. So this is. But you will see we're getting very close to the structure that we had for solitons. Soliton, this is the kind of an object that there was this kind of a term which we finally got as a boundary term, because boundary there was there was only one space integral there, and it picked up the boundary values, which was a topological, gave us a topological charge. This object, instead of being one-dimensional integral, it's a three-dimensional space integral, and we are getting only the properties of these objects at the boundary r equal to infinity. Now depending upon what b is and phi is at r infinity, this quantity can have a non-trivial value, and that non-trivial value is the topological charge, and that we will see is the magnetic monopole charge.